of matter, of nature, are becoming very real because we're beginning to be able to access this tremendously complicated configuration space to do useful things, to make calculations that are useful to us.
So Professor Brian Cox just went on The Big Think, and he spoke about quantum mechanics and quantum computers for almost an hour and a half. I got a chance to listen to that interview, and there's a couple pieces of it that I thought pertained to quantum computing specifically, and I wanted to do a little bit of a react. So this should be a fairly quick video. We're going to just watch a couple things about the double slit experiment. We're going to learn a little bit about qubits, and then we're going to hear Brian's thoughts on quantum computing and how all of these quantum mechanic principles are being applied to building modern quantum computers.
I'm Brian Cox. My full title is Professor of Particle Physics at the University of Manchester, Royal Society Professor for Public Engagement in Science and Visiting Scholar at the Crick Institute. And perhaps the best introduction would be to think of a property of particles called spin. So you might call these things a qubit. So what is a qubit? So you think of a coin, which you would toss in the air, and it can be either heads or tails. So that's a kind of an intuitive picture of the world. This thing is either heads or it is tails. Now, a quantum coin could indeed have the property that it would be heads or tails. But the difference between quantum mechanics and classical theory is that an object like a coin, a quantum coin, can also be in what we call a superposition of heads and tails. So that means that it can be in a state where it is, let's say, if we observe the thing, we'll talk about that a bit later, but it can be in a state where it could be 30% heads and 70% tails, or 40% heads and 60% tails, or any combination, any mixture of heads and tails. And that is a perfectly legitimate description of the state of the configuration of this thing.
So the easiest way to look at this is how a classical computer works. So on, off, binary. That's essentially what is happening in a classical computer, but in a quantum computer, in the quantum state, can be both on and off at the same time, which is what Brian's explained here. So now let's learn about the double slit experiment.
Let's say you have something that will emit, let's say electrons, so particles, electrons, electron gun that emits particles. And then you have a barrier that has two slits cut in it and a screen. So that's the setup of the experiment. So we have something that emits electrons, two slits cut in a screen, and a detector, another screen that the electrons will hit. So you fire the electrons out. So what will that look like? Well, if you think of the electrons as just little particles, little bullets, let's say, that are emitted from this gun, then you would imagine that the electrons can go through one slit or the other one, depending on how they come out. And you can imagine that they might get deflected around a little bit when they go through the slits. But basically, on the screen, you would expect most of the electrons to appear opposite one or the other of the slits, with maybe a bit of a spread because they rattle around a bit when they go through. So you get lots here, and pretty much none in the middle. But that's not what you see. What you see is a very clear pattern on the screen. You see sort of stripes, a stripe on the screen where you get lots of electrons, and then a stripe where you get very few or none, and then another stripe where you get lots, and then a stripe where you get very few or none, and then another stripe, and then very few or none. So you get this stripy pattern. That pattern is exactly the same pattern that you would get if you sent waves through the slits. Let's say water waves, any kind of waves. Then it's easy to understand. Because what's happening then, and physicists knew this back in the 1700s, right, is that you can consider each slit as a source of new waves. And the waves come out, and waves have the property that they can interfere with each other. So you can get the peak of one wave arriving at the screen from one slit, and a trough of a wave arriving at the screen from another slit. And if everything's lined up correctly, the peak and the trough cancel out and you get nothing. So you get this property where something from each slit, it's very easy to understand if it's a big extended wavy thing, lines up in such a way that it cancels out. And then it could line up in such a way that it reinforces and you get a big disturbance there. And then it cancels out again and then it reinforces again. So you can imagine this stripy pattern on the screen. That's what you get with waves. The fact that you get it from particles is interesting. But here's another interesting thing. You still get that pattern if you send one particle at a time through the slits. So it is, and let me use my language carefully. I was going to say it is as if the electron can somehow explore both paths, just like a wave can, and then interfere with itself to control where it lands on the screen. As if is something that people might object to. Many physicists would say, no, it does. So the statement is that the electron explores both routes at the same time, at once, let's say, on its route from the electron gun through the slits to the screen. So that's a very strange picture of reality. We surely think of particles as following definite paths. And it might be that you don't know quite which path it's going to take, but surely you would say, in reality, it will go one route or the other route. But that experiment, which I emphasize has been done now many times, tells us that nature is not like that. It tells us that the electron must, in some sense, explore all routes on the way from the gun to the screen. But I suppose the problem comes when you say, well, what does it mean? Does it really mean? Is it just calculational? Is this just mathematics? Or does it really mean that the electron explores every possible route? And by that, I mean every possible route. You might consider it going to the Andromeda galaxy and back. Right? Every possible route on its journey from when it's emitted to when it's detected. And I think many physicists now would say that that is a correct description of reality.
The rules of the physical realm and the rules of the subatomic realm appear to be, or the atomic realm, I should say, appear to be very different, and it requires us to think about things in a different way. He's very careful with the language he uses, and he's also saying that there are more and more physicists today that agree on this explanation, implying that there hasn't always been agreement.
But now, particularly I think, with the possibility of building quantum computers, this attempt to understand how large systems of quantum mechanical objects behave is becoming extremely important, because a quantum computer is a device which is built out of qubits. So remember, a qubit, an example would be an electron, which has this property that when you make an observation of the spin, let's say, of this electron, it behaves like a coin. It can be up or down, heads or tails, however you want to describe it. But that thing can also exist in a superposition, a combination of these things. And it's a perfectly valid configuration. And you use that. That's the kind of property that you use in building a quantum computer. You can also then ask the question, well, what happens if I get another one, two electrons together? These can be in what's called an entangled state. So then you have a much richer structure of this physical system. And I separate these electrons. I take one to, let's say, to Pluto and leave one on planet Earth, right? Same for the other one. If I go to Pluto and have a look at this one and it's down, then this one definitely is up, right? So this is called quantum entanglement. And the reason it bothered Einstein and others is it would appear that something is instantaneously changing. And it's not just your knowledge of the system that's instantaneously changing. It would seem that the system itself is instantly configuring itself when you make some measurement.
These technologies are not just theoretical, they're practical, and we're actually building machines with them and those properties. And these entangled states are where the magic happens.
You might say, well, this is nonsense. There must be something else. And it turns out that as far as we can tell, and a Nobel Prize was awarded for some of this research a few years ago. Then no, there's nothing hidden there. This is the way that the system is. But you think about that system of 2 qubits. Right? Think about it. So you've got these two things which can be up or down. There are 4 possible combinations of that system. You can have up down, down up, up, or down down. 4 for the 2 qubit system. For a 3 qubit system, you think about it, ups and downs, you'll find out there are 8 possible combinations and all mixtures of them. For 4 qubits, then it's 2 to the power 4. There's 16 possible combinations. We're talking about building quantum computers now in which we have 100, 200, 300 qubits, all in principle entangled together. The number of possible descriptions of that system, then, you have numbers that describe it. If there are 100, it's 2 to the power 100 different configurations and any mixture of those things that are states of the system. So pretty soon, 2 to the power 100 for 100 qubits. What's the number of atoms in the universe? If you had 2 to the 500, you'd far exceed 500 qubits. The number of numbers you need to describe that system exceeds the number of atoms in the observable universe. But it's a thing that we can build. We can build just about. We're not far off being able to conceive, at least, of a network of 500 qubits. They're physical things. They're kind of like that big, some of them, right? So you have 500 of them in this room. So the power that's hidden in the description of a system like that is immense. And the thing that a quantum computer does is it uses that power, some of that power, some of that vast computational or configurational power of the thing. It's very, very difficult to do. And we've not been able to do it particularly well at the moment. You'll read many papers online where obviously companies like Google, Microsoft, IBM are investing a lot of money in these devices because potentially they can carry out computations that no conceivable classical computer could make within the lifetime of the universe because of this tremendous freedom in the description of the structure of the system. So quantum mechanics and quantum entanglement, these properties of matter, of nature, are becoming very real because we're beginning to be able to access this tremendously complicated configuration space to do useful things, to make calculations that are useful to us.
I don't think the builder or the creator of this system ever intended for the system to understand itself at this level.